For the final project of ECE 5115, students were asked to connect an EEG machine to a drone and have the drone fly between two vertical obstacles. For this project, students were given a Parrot Rolling Spider mini drone and a Muse 2016 headset model MU02. Before starting, a lot of research was done to find the optimal solution given our hardware. The first challenge was connecting the headset to the computer. During the midterm, connecting a drone to a Mac was a simple process, but required a dongle for Windows. The headset had the opposite problem. Windows computers connected seamlessly, while Macs required a dongle. After having purchased a dongle for the Windows computer for the midterm, it was decided that the final would be on a Windows computer. The bulk of the research was on programs to connect the headset to Simulink. We found several options. First was MATLAB OSC. It required both a Windows and a Mac computer, and because we're turning this in, we didn't want to use a two-computer setup. Then there was Muse.io. This program was created for a 2014 headset, and we had a 2016 headset. MuseLab gave us an OSC output. The OSC data format isn't compatible with MATLAB, so this wouldn't work either. We got a little closer with Muse Player. This option would save the data as a MATLAB file, but because it sends packets of information, the changes would be delayed, and we wanted the drone to be affected in real time. Finally, we found Muse SDK. As we looked through the Getting Started portion on the Muse developer page, they had a program that would read the data from the EEG and display it on screen. We changed the code a bit so that every time it read out data, it would also send that data in an array to Simulink in a UDP format. After we decided on a program, we began working on the project. During the midterm, we used a signal builder block to change the XYZ coordinates on the drone. We replaced that block with a UDP receiver block that comes with Simulink. We took the EEG data and put it into a bus so that way we could manipulate it from there. We used a graph to see the output and found that the most reliable data came when the user blinked. We used these graphs again in the next step while reading the data. To make the data useful, we had the blinking activate a series of events. First, hovering, then flying forward, and finally landing. We did this by utilizing if statements and having the blinking correlate to the changing in the XYZ axis. When the EEG data went above a threshold, the next if statement would trigger. The XYZ coordinates would then go into a feedback loop in the control system that was created during the midterm. This was a control system using the ASB quadcopter control system as a base. The main bulk of our testing and experimenting came from the initial research of the parts and programs. The ASB quadcopter control system that comes with Simulink was used as a base for our control system. The main bulk of our testing and experimenting came from the initial research of the parts and programs. The blinking threshold also required testing. We wanted the user to have to hard blink so the drone would not stop or start accidentally. Overall, this led to a successful run.